Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. The Lie algebra is a gadget which captures infinitesimal information about a Lie group. And that infinitesimal information includes both the geometry and the group structure. And it's a natural question to ask, well, if you have that infinitesimal structure encoded in the Lie algebra, how can you use that information to study the Lie group? And that's what I want to show you in this video here. Okay, and the key will be this theorem that I'm going to present to you right now. So we're going to consider now two Lie groups, G and H, and we'll use the small Gothic letters, Gothic G, Gothic H, to be their Lie algebras. So remember, that's the tangent space to those Lie groups at the identity, and we put this Lie bracket structure. So these tangent spaces, you can use that to generate left invariant vector fields on G and H, and then you have the Lie bracket of those vector fields. Okay, so that gives you the Lie algebra structure. Okay, so suppose we look at these Lie algebras, and the information we're given is a linear map between them, psi, from Gothic G to Gothic H, and let's suppose that's a homomorphism of Lie algebras. So what's a homomorphism of Lie algebras? Remember, you have this Lie bracket here, so it's a type of multiplication, non-associative multiplication here, and also a non-associative multiplication here. You just want this linear map to also preserve that Lie bracket. So another way of saying that this is a homomorphism of Lie algebras is that, well, remember, from these Lie algebras, okay, so they give you vector fields and hence differential operators. You can look at the ring of differential operators generated by these. That will give you the universal enveloping algebras, U of G and U of H. And we know that since these are generated by these universal enveloping algebras are generated by these Lie algebras, okay, this map will give you at most one algebra homomorphism from here to here. Okay, and to check that it actually does give you an algebra homomorphism, you need to check that the relations here get sent to 0 here. Okay, the relations in these generators. Okay, and of course, if you figure out what that means, it just means that this map psi preserves the Lie bracket. Okay. So if you're given this data that's just about the Lie algebra, it's going to actually tell us something about the Lie groups G and H. Okay, so what you would like, of course, is to say that there's a map from G to H. Okay, that's what you'd like. Unfortunately, we don't get there. We do get a map to H. Okay, there's going to be a Lie group homomorphism to H, but it's unfortunately not from G necessarily. Okay, it's only from G tilde, which is a simply connected cover of G. So remember, this G, any Lie group, you can look at its simply connected cover, okay, and that will be a Lie group as well, as it turns out. And you can have a Lie group structure on this such that the natural projection map onto this Lie group is actually a Lie group homomorphism. Okay. What else you know about this map is that these actually have the same tangent space. So actually these will have isomorphic Lie algebras. Okay, so you have this Lie group homomorphism from G tilde to H. Well, of course, you might say, well, you can always easily construct such a Lie group homomorphism, some Lie group homomorphism from here to here. You just send everything to 1. But of course, this phi is going to be related to this psi in a certain way. Okay, and how is that? Well, if you look at the derivative of phi at the identity on G tilde, okay, if you look at that derivative, okay, so that has to be mapped from the tangent space here at 1, so that's basically the Lie algebra G, Gothic G, to, and the image of 1 here, since this is a Lie group homomorphism, is 1 here, so it maps to the tangent space to 1 of H, so that's this Gothic H here. And this derivative map at 1, okay, this tangent space map is just the original one here. So in other words, we think of this as a map on tangent space, so this psi, okay, and what we're saying is that we can actually realize this as the derivative of some map of Lie groups. It's not of the original Lie groups G to H, okay. Unfortunately, you may have to alter the G a little bit here to its simply connected cover, G tilde, okay, but otherwise it's about as good as you can get, okay. So that's the key theorem. So I can't present the proof for this theorem here, it would take too long, but I can give you the key idea as to why it's true. Okay, So let's see the data that you have here. Okay, we have the algebras, Gothic G, Gothic H, and we have the map between them, psi. The other thing we have is that we have an exponential map from the Lie algebra to the Lie group. Okay, so this Gothic G gets mapped by the exponential map to both this G here and G tilde, because this is also the Lie algebra of G tilde. Okay, so there's a map here, and there's an exponential map from Gothic H to this Lie group H as well. And the other thing we know about this exponential map is that this is a local diffeomorphism. Okay, so if you're in a small open neighborhood of 1 of this simply connected group G tilde, okay, let's suppose you're out here like this. If it's sufficiently small, open neighborhood of 1, that will be diffeomorphic to its inverse image under the exponential map. So that's some open neighborhood of 0. Okay, so that point there will get mapped to something inside G given by, say, a vector like that. Now, once you have this vector here, you can apply this psi map, this linear map here, to give you a vector over here. Okay. And then you can apply the exponential map to get you back down to some element of H here. Okay. And it turns out that this map phi, if you restrict it to this open neighborhood U of G tilde, okay, it's going to be given by this composite going around like this. Okay. So the key point is, well, how do you try to extend this map to the whole of G tilde? So you've defined it on some open neighborhood of the identity, right? Okay, well, remember, it's meant to be a group homomorphism. So if you have a product of 2 elements inside this open neighborhood, of course, how do you define where they get sent to? Well, you know where each of them goes to, so it gets sent to the product of their images, which are defined. So if you have it defined on this U, you'll also have it defined on U squared, so to speak. Okay, so the set of all products of elements of U with something in U. And similarly, you can define U cubed, U to the 4th, and so forth. So you can define it on the union, basically on all, actually you can also define it on U inverse as well, because this has to preserve inverses. Okay, so you can define it on anything which is a product of elements inside U and their inverses. Okay, and if you work out what that is, because U is an open set, okay, and you look at the unions of all these products and things like that, it will turn out that this is going to be something that's both open and closed. So since this G tilde is connected, you will find that the union of all these products of U's with their inverses, that will give you the whole of G tilde. So that will tell you basically what is the unique way of defining what this map is from G tilde to H. Okay, and I guess the big thing though is you have to check that this is actually a well-defined group homomorphism. So that's a rather complicated thing. So rather than going through that, I want to show you an example that we've actually seen in this playlist before. Okay, so here the group that I want to take is the circle group S1, and so this circle group you can think of in many different ways. For this particular example, I want to think of it as a quotient group. So we start with the Lie group R, and we're going to mod out by this subgroup Z. Okay, and it's a discrete subgroup, so you can talk about that quotient Lie group. Okay, so there you have that quotient Lie group. Okay, so what's its Lie algebra? Okay, so what's the left invariant differential operators? Okay, so the left invariant vector field, of course, you just have a constant vector field that's given by d dx, and you scale it to whatever real you like. Okay, so that's the Lie algebra. It's just basically a copy of R. That's a Lie algebra. Okay, so this Lie algebra, it's going to be a one-dimensional vector space over the reals. And I guess you should also look at the Lie bracket. Okay, so the Lie bracket in this case here happens to be trivial. Okay, the Lie bracket of any 2 vector fields is going to be 0. And that's because, remember how you take this Lie bracket. Okay, you look at the commutator between 2 differential operators. Okay, so some constant multiple of d dx and some constant multiple of d dx. Well, they of course commute. Okay, so since they commute, the Lie bracket will be 0. Okay, so the final thing we need to have all the ingredients in this key theorem. Okay, so we need a Lie group. Okay, so another Lie group. Okay, the codomain Lie group H, and it's Lie algebra. We also need the simply connected cover. So the simply connected cover in this case is kind of given to you here already. So this R is simply connected, and it's of course the simply connected cover. So R is that Lie, simply connected Lie group, which is a simply connected cover. Okay, R. Okay, so let's have a look at the universal enveloping algebra of this Lie algebra. And we've also seen what this is before. If you look at all constant multiples of d dx and you let it generate an algebra of the reals, what do you get? So you can get all higher derivatives, so d to the n dx dn, okay? And that's by composing them. And of course you can get linear combinations of all of them. So in other words, it's a set of all constant coefficient differential operators. And the nice way to write that, so you see the algebra structure here, is it's basically just a polynomial ring in d dx. Okay, so we'll write it like that. The polynomial ring with real coefficients in the variable now is this differential operator d dx. Okay, normally you think of this as not usually commuting, but since all the coefficients are constant, okay, all these differential operators will commute here. Okay, and now let's look at the setup that we have here. Okay, we want to look at this setup, which is just a linear map, which is a map of Lie algebras. So we're going to consider any v inside H, okay, and we're going to consider the linear map, which, well, this is just a copy of R, right? It's one dimensional, so I just have to say where the basis vector d dx goes to, and let's send it to V. So there's a unique linear map like that, okay, and I claim that this is actually a Lie algebra homomorphism, this one here. Now you can do it either using the definition, what is the Lie bracket of two vector fields. Here, okay, Lie bracket of two elements here is 0, okay, so you need to make sure that it gets sent to 0. There's an easy way to do it actually, and that's just to use the second description I have here, and that is that this induces a algebra homomorphism. Okay, so what's the algebra homomorphism? Okay, so if d dx gets sent to V, well, what's an element in the universal enveloping algebra? It's just a polynomial p in d dx. So what I can do now is I can just look at that same polynomial in V. Okay, and hopefully you know since this is just a polynomial ring in one variable, okay, and by the universal property of the polynomial ring, that this is automatically an R algebra homomorphism. Okay, to describe an R algebra homomorphism from this polynomial ring in this one variable d dx, okay, all you have to do is if you want to map it to another R algebra, you just have to say where d dx goes to, and it can map to anything you like. Okay, and that's that will automatically define. This is actually the definition for what that algebra homomorphism is. Okay, as you can easily check. Okay, so that's great. We have a Lie algebra homomorphism. So we have all the hypotheses here satisfied, and that means now we can have this Lie group homomorphism from G tilde to H, such that its derivative is going to give me back this map here. Okay, that's what's going to happen. The derivative will give you back that map here. Okay, and so I'm just going to tell you what this Lie group homomorphism is. So this Lie group homomorphism goes from the simply connected cover, which is R here, to H. But a Lie group homomorphism from R to H, essentially, at least if it's non-trivial, is going to be just a one-parameter subgroup. So it's this one-parameter subgroup, so T here is going to be my one parameter, and it's related to V, which is inside the Lie algebra of H. So I hope you can guess what it is. It's the corresponding one-parameter subgroup associated to this vector field, left invariant vector field, that's given by this V inside H. Okay, so it's quite easy to see what's going on here. If you want to differentiate this, okay, if you want to do d phi, essentially you just differentiate this with respect to t. Okay, and when you differentiate it with respect to t, of course, what's the vector that comes back out? It's V. Okay, so that's why the derivative of this phi is indeed what you want here. Okay, it is this psi. Okay, and that shows you a case where we've actually seen this key theorem in action, and the point is that it works more generally, not just for this example here. Okay, but if you have any Lie group, okay, and then here unfortunately you have to put the simply connected cover. So I guess Lie group here should be connected if you talk about the or alternatively, you can look at the simply connected cover of the connected component of the identity here. Okay, so that's great. So let me just say some words about why we can't always expect a map from G to this H. Okay, so why is that the case? You can't always expect that to be true. Okay, so do we get a map from this S1 to H? Okay, can we factor this one that way? Okay, so that's what we want to do. Okay, and let's see when you can do that. Well, when can you do that? Well, the point is that here you've got the map from R to H, and you want to make sure that all of Z has to get sent to, because all of Z is the identity in here, that's the identity coset, that has to get to send to the identity here. So that means that since this Z is generated by 1, the condition for this to induce a Lie group homomorphism from S1 to H is that phi of the number 1 here, okay, the real number 1, which is inside this Z, okay, is the identity in H. So in other words, that's going to be phi of 1 is just equal to x per v. Okay, and of course there's no reason why x per v should equal 1 necessarily. So sometimes this will happen. Okay, so if this happens, if you know that this happens, okay, you will get a Lie group homomorphism. But that also tells you one way, if you want to try to get a Lie group homomorphism from G to H, one way to do it is, first you build the Lie group homomorphism from G tilde to H, and then see whether this holds here. I now want to give a wonderful application of this theory to the representation theory of Lie groups, or at least the finite dimensional representation theory of Lie groups. And the basic idea I want to get across is that this theory more or less reduces to the study of the modules over the universal enveloping algebra of the Lie algebra of that Lie group. Okay, so let's start with a simple example. Okay, so suppose we have G here is SU2. That's the simplest, interesting and non-trivial Lie group. Remember, this is simply connected. We can look at its Lie algebra. So it's given by, since it's hard to write the Gothic SU2, I'll just use the double underline here, SU2 like that. And this is going to be a subset of 2 by 2 complex matrices. Okay, it's going to be which of these 2 by 2 complex matrices? They're the ones such that its adjoint A star, so remember that adjoint is just the conjugate transpose equals its negative, and also the trace is equal to 0. Okay, so the unitary gives you this condition here when you differentiate, okay, and the determinant 1 when you differentiate gives you the trace 0 condition here, okay. And so this is a Lie algebra. In fact, if you want to work out what is the Lie bracket here, remember this will actually be given by just the commutator. Okay, so basically, if you have A and B are 2 elements satisfying this condition here, then the Lie bracket will be AB minus BA. Okay, and you can check that this condition still holds. Okay, so what's a finite dimensional representation of actually any Lie group here? Let's suppose it's over C. That's just a Lie group homomorphism from G to GLNC. Okay, so as usual, this is the set of automorphisms, Celian automorphisms of n-dimensional space over C. Okay, so this also gives you a G module structure on C to the n, and so you can also think of the corresponding G module as well. Okay, so we'll also call that a finite dimensional representation of G. And of course, you can do this in a coordinate-free way as well, if you like. So you can replace the GLNC with GL of some finite dimensional vector space over C instead. Okay, since we're looking at homomorphisms from here to here, and in this case I've picked an example where G is simply connected, the key theorem tells you that, well, you just have to look at the Lie algebras. Okay, so we just need a Lie algebra homomorphism from the Lie algebra here, which is Gothic G, to the Lie algebra here, GLNC. And remember that Lie algebra is going to be just the Lie algebra, the vector space of n by n matrices over C, and the Lie bracket is given by this commutator I already mentioned. Okay, and so the link between these two, of course, is that this psi will be the derivative of this phi. Psi equals d phi. Okay, so of course, to give a Lie algebra homomorphism, I just need to say basically give a lift of this to the universal enveloping algebras. And since this is actually defined over the complexes, there's a little bit of subtle things going on with complexification here. What we can do is, instead of looking at this Lie algebra here, we can complexify it. Okay, so we can tensor over R. This is a real vector space. It's a real Lie algebra. It's a vector space. You can tensor over C. And basically all this does is you're looking at the C linear span of all of these matrices here. And it turns out that, of course, this condition here is C linear, but this one is not. Okay, so this one here, what happens when you take the C linear span is that this condition disappears, and you just get basically the traceless condition here. Okay, this is the condition that you have here. So in this case here, this is something that's defined over the complexes, and so this you can look at the C algebra generated by this Lie algebra. Okay, so that's I can denote by U of SL2C, since it's the algebra, but over the complexes now. This is a C algebra, and essentially you're just looking at homomorphisms from here to the universal enveloping algebra here, where SL2C maps to this GLNC. Okay, so that's rather nice, is that you can look at it just by looking at the universal enveloping algebra. You can study finite dimensional representations of this Lie group here. Okay, what about Lie groups which are not simply connected? Well, I suggested to you the way you can study them before. So let's look at an example related to this one here. Let's look at SO3, the Lie group of determinant 1 orthogonal transformations of three-dimensional space. And one rather nice fact about this is it's related to SU2 in a very simple way. In fact, SU2 is a simply connected cover. Okay, so this is isomorphic to SU2 modulo some discrete subgroup, and in fact the discrete subgroup that you look here is just plus or minus 1. Okay, since these are 2 by 2 matrices, okay, so this is even dimensional. Minus 1 also has determinant 1, okay, and it's certainly unitary as well. So you can mod out by this normal subgroup, okay, and it'll be isomorphic to that. And if you want to see why this holds, you can have a look at my video on spinors. Okay, so that's something that you have. And so essentially, if you want, instead of a homomorphism from SU2 to GLNC, but to SU03 to GLNC, you just need a homomorphism from here to here. So by the universal property of quotients, homomorphism from SU2 to here, such that it's trivial on plus or minus 1. In other words, it's trivial on minus 1. Okay, that's all you need. So essentially, representations of SO3, they're all the SU2 representations, at least the finite dimensional ones we're considering here, which are trivial on plus or minus 1. Where -1 acts trivially. Of course, I'm illustrating some fairly general sorts of ideas here. Okay, so let's see more generally what's going on. So suppose you have any simply connected group, not just SU2. So G is some simply connected Lie group. Okay, let's suppose you want to have the G modules over C. Okay, suppose you want the n-dimensional ones. So the ones that come from Lie group homomorphism like that. Okay, there essentially you can just reduce that study to just modules, finite dimensional modules over the following universal enveloping algebra, UG subscript C, which I'm going to define to be, well, you look at this universal enveloping algebra U of G, and you just complexify. Okay, so you tensor this with C, so you get some C algebra that way. Okay, so this is rather nice. Okay, this addendum really tells you, okay, if you want to study these finite dimensional representations of G, okay, then really all you have to do is you just have to look at these finite dimensional modules over this C algebra, and this C algebra is finitely generated. So this is really just an algebraic problem. Okay, so we've reduced this representation theory for this Lie group, fairly complicated manifold, to straight algebra. So let me kind of indicate why this is true. I won't give you the complete reason, but the main gist of the idea of what's going on is the following. Okay, so you're looking at homomorphisms like this. And that's given by the Lie algebra ones. Okay, so Lie algebra maps from G to GLNC, which I remind you is n by n matrices in C. And these you can lift. Okay, to be a Lie algebra homomorphism just means that you can lift this from the universal enveloping algebra here to the universal enveloping algebra over here. Okay, and the key thing that I want to do is I want to show you that there's this wonderful map from this algebra, C algebra here, algebra of the complex over here, to M and C. This is we see this is a Lie algebra, but of course it's just a normal C algebra as well. Okay, you can multiply just as per normal matrix multiplication, and that's an associative multiplication, as opposed to the non-associative Lie bracket that you have here as well. That comes from the associative multiplication. Okay, so there is actually a algebra map from the C algebra to this C algebra here. And what is it? It's quite easy to say what it is. So I just need to define it on the generators here. And the generators here are elements inside this Lie algebra. So basically they're just n by n complex matrices, A. And I'm just going to send A to A. Okay, that's the most natural thing that can happen. And then it turns out that if you send this generator to itself, okay, and you just see what it generates, then this will be an algebra homomorphism. Okay. So if you have this algebra homomorphism, that means that given a G module, you'll have this map like this, and hence you'll have a homomorphism from here all the way down to here. Okay, a C algebra homomorphism. But what is an algebra homomorphism from this C algebra to MNC? Okay, that's just basically an n-dimensional representation of this algebra here. Okay, that's all there is to it. Okay, so remember, if you have a homomorphism from UGC to MNC, okay, that tells you an n-dimensional module. Okay, it's C to the n is the module, and how does any element here act? You just map it to this n by n matrix, and that tells you how left multiplication acts on C to the n. Okay, and conversely, you can also see that if you have a map from here to here, so that's going to be given by some n-dimensional module over this universal enveloping algebra, you can actually lift it back up here. Okay, and I'll show you the rough idea. So the thing is that, yeah, why do you get an algebra homomorphism going through here? Okay, well, I've told you what happens on all the generators, and the only obstacle to this actually giving you a well-defined algebra homomorphism is, well, you know what happens on the generators, but those generators aren't free. Okay, they have relations between them. So you want to make sure that the relations here get sent to 0 there. So let's check to see what the relations are. So remember what the relations are in the universal enveloping algebra. Okay, so they all have this form, given any pair of elements in the Lie algebra, so any pair of generators, A, B inside GLNC, okay, the relations have the form, when you multiply inside, so the star I'm going to use to be multiplication inside the universal enveloping algebra. So A star B minus B star A is equal to, you look at the Lie bracket of A and B inside GLNC. Okay, so that's some element inside here. So this commutator equals this Lie bracket. That's the relation. Or in other words, A star B minus B star A minus the Lie bracket of A and B equals 0. That's the relation inside here. And as A and B vary, you get all the relations that way. And you need to say that, well, if you use this map here and you force it to be an algebra homomorphism, then this relation had better go to 0. Okay, that's what you want. Okay, so A gets sent to A, B gets sent to B. Okay, and then you multiply inside here. So that's matrix multiplication. So this A star B gets sent to AB, matrix multiplication. And this B star A gets sent to the matrix product of B and A. And this Lie bracket of A and B, that's some element inside this Lie algebra. So elements inside the Lie algebra, that's a generator, just gets into itself. But what is the Lie bracket of A and B? Okay, so that's inside here. The Lie bracket of A and B is just AB minus BA, which is precisely this term here. So when you subtract it off, you get 0. So that tells you that this is a well-defined map from here to here. Okay. And then similarly, if you have a map from here to here, then GC gets mapped to here. And this is GLNC, so that gives you a map from G to GLNC. And you just have to check that it satisfies it is a Lie algebra homomorphism. And this same type of argument will show that. So at the end of the day, what this addendum really tells you is that, yeah, if you want to look at finite dimensional modules over some simply connected Lie group G, all you have to do is you complexify the Lie algebra, look at its universal enveloping algebra, or you just look at the universal enveloping algebra and you complexify it, and you just look at finite dimensional modules over this algebra. I hope you enjoyed this adventure in pure mathematics.